everyone, today we're presenting on gas chromatography-mass spectrometry, also known as GCMS. As the name implies, the first part is gas chromatography, and you can see the entire machine here. However, before the sample can be injected into the port of the machine, it must be prepared. Organic chemists often use a solvent to dissolve the sample in. Then it's injected into the machine, where it immediately volatilizes into gas state. After entering, it goes into the GC column during the mobile phase, in which carrier gases such as helium, nitrogen, or hydrogen propel it down the column. And this is also called the stationary phase because there are samples around the walls of the column interacting with the solvent and slowing it down, allowing time for the oven's temperature to increase. This gradual increase in temperature allows compounds with a lower volatility or boiling point to elute sooner. When they elute, they'll reach the detector, resulting in a chromatogram, where you can see the retention time on the x-axis and the relative abundance on the y. The retention time is the time from which the compound enters to the time to which it exits the GC column, and each compound's retention time is unique, lending clues about its identity.
After the compounds leave the GC column, they enter the mass spec detector. And the mass spectrometer passes a high energy beam of electrons through each compound, knocking off electrons in the compounds and producing ionized fragments, usually with a +1 charge. And these fragments vary in size. Then the ionized fragments are accelerated through the electric plates, and these are represented by the purple circles on the diagram, before reaching the magnetic field. And the magnetic field filters these fragments based on their mass, and this is because the magnetic field deflects or bends the path of ions to different degrees based on their mass. So heavier fragments are deflected less, and lighter fragments are deflected more, so their path gets more bent. And then these ionized fragments collide with the charge detector located at the end of the tunnel, where their mass to charge ratio and relative abundance are calculated. So the detector basically measures the abundance of a certain type of compound that hits the specific spots on the detector. And this data is organized in a mass spectrum. So it displays the signal intensity or abundance of each fragment on the y-axis, and on the x-axis it shows the m to z ratio. And that ratio is just the mass of the fragment divided by its charge. And since the charge is usually +1, the m to z ratio is usually just the molar mass of the compound. And if the charge is greater than 1, say +2, then you would divide the mass by 2 and you would get the molar mass. And this is how you can measure the abundance of a certain compound in your sample. And then the computer on the GCMS matches the sample's mass spectrum, which is just this graph, to other mass spectra in a database and reports a list of likely identities based on how close the matches are. And next, we'll talk about the comparison model. And here you can apply this picture to both MS and GC. So for GC, the larger pebbles will, after you shake the strainer, the larger pebbles will stay in the strainer, and then the lighter ones will get strained out based on how small they are. So the smaller ones will fall out sooner, so they have a smaller retention time, and then the larger ones will have a longer retention time. And in the mass spectrometer, this also applies as the electric field will separate the compounds based on their mass. So as you can see, the smaller grains of sand are separated from the larger ones, which is comparable to the magnetic field bending the paths of the fragments to a certain degree. And then we'll talk about the applications of this technology. So one use of it can be in newborn screening tests, where you would screen a sample of the newborn's blood, and you would test for the presence of certain molecules that indicate metabolic disorders. And this can also be applied to drug screening, where you would either screen urine or a blood test to test for, again, the presence of certain molecules or drugs.
Another one of GCMS's applications is in oil or gas analysis. When producing petroleum or natural gas, testing is required to check the content of various components, which could include sulfur, cyclohexyl acrylate, and SIMBRs. GCMS is also used to study complex metabolomics, and it's similar to newborn screening tests, except that it's used to identify metabolites in new organisms that are found. For example, it could be a plant, a microbe, or an animal. That's it for today. Thank you for listening.